Now here we need to diagonalize this matrix A. When the matrix is diagonalizable, if there exists an invertible matrix, let's say P, such that P inverse AP should be diagonal matrix, right? So we need to find first such matrix P. How do we find that matrix? For that, first we need to find the eigenvalues for this matrix and then the eigen vectors. From there we get the bases, right? And then from those bases we find the matrix P, right? So let's start with the solution. So this is the matrix given to us. We need to find first the eigenvalues for this. For that, just write the characteristic equation first to get the eigenvalues. So the characteristic equation of A is the determinant of lambda I minus A is equal to 0. We need to solve this, where I is the identity matrix of the kind 3 by 3, right? Just multiply lambda with this. We get lambda 0 0 0 lambda 0 0 0 lambda, and then we need to subtract this A matrix from this matrix. And now we need to find this determinant, that is the determinant of lambda I minus A. So that is lambda minus 1, and then 0 minus minus 3, that is plus 3, and then 0 minus 3 minus 3, and then 0, and then lambda minus minus 5, lambda minus minus 5, that is lambda plus 5, and then minus 6, likewise it is 0, and then 3, and then lambda minus 4. So finding the determinant of this, now solving this determinant, we get lambda minus 1 into, cross multiplying these two, we get lambda minus 4 into lambda plus 5 minus 3 into minus 6, that is minus 18. So this becomes plus 18 minus 3 into, cross multiplying these two, we get 0, minus 3 into, cross multiplying these two, we get 0. That is lambda minus 1 into, multiplying these two, we get lambda square minus 4 lambda plus 5 lambda, that is plus 1 lambda minus 20. So this is lambda square plus lambda minus 20 plus 18. So that is minus 2 equals to 0. Factorizing this further, we get, this is lambda minus 1 into lambda plus 2 equals to 0, or it can be written as lambda minus 1 whole square into lambda plus 2 equals to 0. So from here we are getting the eigenvalues to be lambda equal to 1 of multiplicity 2. It's having the power 2. Let me write this as first eigenvalue, and then the second eigenvalue to be minus 2 of multiplicity 1. Very fine. Okay, so let's find the eigenvectors for these two eigenvalues when lambda 1 equal to 1 for the first eigenvalue, right? How to find the eigenvectors? For that, we need to write the homogeneous equations to be lambda I minus A into x equals to 0 for the first eigenvalue lambda 1. So we have already calculated this over here, and we just need to put the first eigenvalue lambda 1 equal to 1 in place of lambda. So we get 0, 3, minus 3. In the second row we get 0, 6, minus 6, and in the third row we get 0, 3, negative 3. So this is 0, 3, minus 3, and then 0, 6, minus 6, and then 0, 3, minus 3. And for x we write the column vector x1, x2, x3 and is equal to 0, 0, 0. From here we get the three homogeneous equations. So we get the first equation to be as 0 into x1 plus 3 into x2 minus 3 into x3 equals to 0. So this is 0 into x1 plus 3 into x2 minus 3 into x3 equals to 0. That is, we are getting x2 minus x3 equals to 0, or x2 is equal to x3. This is the first homogeneous equation. Similarly, we get the second one, 0 into x1 plus 6 into x2 minus 6 into x3 equals to 0. So this is 0 into x1 plus 6 into x2 minus 6 into x3 equals to 0. So from here also we are getting x2 equal to x3. Likewise, the third equation, that is 0 into x1 plus 3 into x2 minus 3 into x3 equal to 0. So the same as the first one, 3 into x2 minus 3 into x3 equals to 0. From here we get x2 equal to x3. So from all these three equations we are getting the result x2 equal to x3. Let me give the value x3 equal to t, where t is belonging to the set of real numbers. So x2 and x3 both are equal to t, right? But there is no x1. So because I need also x1, so let me give the another value x1 to be equal to s, where again s is belonging to the set of real numbers. Right? And now we are writing the eigenvector. The eigenvector x is equal to x1, x2, x3, and this is equal to, what is x1? We have taken this to be as s, and x2 and x3 both are equal to t, right? We can write this vector further as s0, 0 plus 0 t t. When we add these two vectors, we are getting this back the same. If I take s outside, I will be getting 1, 0, 0 inside, plus taking t outside, we are getting 0, 1, 1, where s and t are belonging to the set of real numbers. And these two vectors, these are linearly independent. How do I know that these vectors are linearly independent? Any of these two vectors, if you take any one of these two vectors, suppose 1, 0, 0, it cannot be equal to any multiple of 0, 1, 1. Or if I take the linear combinations of these two vectors to be equal to 0, I will be getting, this implies alpha equal to beta equal to 0. The scalars are 0. All the scalars are 0, right? So when alpha, beta, all scalars are 0, we say that these vectors are linearly independent. So these are x1 is equal to 1, 0, 0 and x2 is equal to 0, 1, 1. And now we are getting the eigenvector for the eigenvalue lambda 2 equal to minus 2. For that, first writing the homogeneous equations. Lambda 2 I minus a into x equal to 0. So we just need to put lambda 2 equal to negative 2 in place of lambda. So we are getting minus 3, 3 minus 3, 0, 3 minus 6, 0, 3 minus 6. So we have here minus 3, 3 minus 3, 0, 3 minus 6, 0, 3 minus 6. For x, we are writing the column vector x1, x2, x3 equals to, this is 0, 0, 0. Right? And now writing the homogeneous equations. So we get minus 3x1 plus 3x2 minus 3x3 equals to 0. That is, x2 is equal to x1 plus x3. This we have got from the first homogeneous equation. And then the second equation, that is 0 into x1 plus 3 into x2 minus 6 into x3 equals to 0. or we can write this as x2 minus 2x3 equals to 0, or x2 is equal to 2 times x3. And third equation would be the same as these two are same rows, right? So we have got this relation from the equation 2, and if I put this value over here, I get this is 2x3 equal to x1 plus x3. If I put x2 equal to 2x3, so that is x1 would be equal to x3. So this is the second relation we are getting. If I take x3 to be equal to t, where t belonging to the set of real numbers, I will be getting x1 equal to t, x2 equal to 2t, and x3 is equal to t because it is equal to x1. x3 is equal to x1, so x3 is also t for t belonging to the set of real numbers. Let's write the eigenvector now. So the eigenvector x, that is x1, x2, x3. So we have got the value of x1 to be t, the value of x2 to be 2t, and the value of x3 to be t. Taking t outside, we get 1, 2, 1 for t belonging to the set of real numbers. So we have got the eigenvector x3 to be equal to, please remember, this is the capital X denoting the third eigenvector, not small x, right? So we have got x3 to be 1, 2, 1. So we have got the third eigenvector to be this, and two more eigenvectors from the first eigenvalue to be x1 and x2. So let's write P to be equal to, let's suppose that invertible matrix to be P, and I'm writing this P matrix to be equal to, writing here the first eigenvector, that is 1, 0, 0, like this. And then writing the second eigenvector, that is 0, 1, 1, right? And then writing this third eigenvector, that is 1, 2, 1. And let's check whether P inverse AP is diagonal matrix or not. So P inverse AP is equal to what? Where we have taken this P to be 1, 0, 0, 0, 1, 1 and 1, 2, 1. From here we get P inverse to be equal to, please find this on your own. P inverse will be 1, 0, 0, minus 1, minus 1, 1, 1, 2, minus 1. Please find this yourself. Thank you. Okay, now finding this P inverse AP. Multiplying this P inverse with first A matrix and then multiplying this with P matrix, you will be getting this matrix to be 1, 0, 0, 0, 1, 0 and 0, 0, negative 2, which is the diagonal matrix. How do we know that this is a diagonal matrix? The first condition for the diagonal matrix to be that it should be a square matrix, right? And secondly, the elements of the square matrix should be 0. All elements should be 0 except this main diagonal. Except this main diagonal, all elements are 0, right? So this is your diagonal matrix. So we have found such P from the eigenvectors such that P inverse AP forms the diagonal matrix. So hence we say that this A is diagonalizable. Right? Okay, thank you. Stay blessed.